All right, so today what we're going to do is we're going to learn about shapes. So
Shapes. Shapes of what?
molecules.
Molecules?
You
We're going to do molecule shapes?
We're going to do British. All right, so we're going to do British. I'm just going to do Canadian. That's all I know how to do. So here's what we're going to do. Up to this point, haven't we drawn a bunch of Lewis structures?
I believe so, yeah.
We've done tons of Lewis structures, and they are flat. The world isn't flat, so we got to work in 3D.
Now, I understand there's this really weird word we have to spell.
Yes, indeed.
Vesper.
Would you write that on the board for me?
VSEPR. What does that stand for?
So we have acronyms all the time. I can't think of, if I'd have been prepared, I thought of a good acronym that we use here for representing something like I'm thinking.
TMI.
TMI, too much information.
Don't do too much TMI.
TMI. This is the same exact thing. Each one of these stands for a particular word, and I encourage you guys to write this down in your notes as you're following along. Valence, shell, electron, pair, repulsion. And that is what we like to call in the business a mouthful. So, what does that mean? You want to take a shot at what that means?
Valence, shell, electron. That would be electrons that are valence electrons, which are electrons on the outer shell. So this means outer shell electrons.
Very true.
Pairs means two, so they must come in pairs, like two dots. We've kind of seen that before, I bet.
We definitely have.
And you're like, you got oxygen with a couple of dots on it, junk like that, maybe a couple extra dots. That's the electron. Repulsion. That means something doesn't like each other.
Yeah.
So you don't like me very much, so we're going to push away.
Indeed. But we do like each other. But the problem is in molecules is that molecules are typically attached with bonds. They can do nothing about it. Let's draw a molecule perhaps. How about if we draw a carbon that is attached to two oxygens, one on either side.
So this is the molecule carbon dioxide.
Yeah, that's carbon dioxide. Now if you notice here, there are electrons on the outside of this oxygen, and there's electrons on the outside of this oxygen. The way it's written right now, these two oxygens are as far away from each other as possible, so they minimize the repulsion. Now, what if we were to draw it like an L shape? You want to draw that on the board as an L shape?
I don't know what you're saying.
Okay, so what if we did this? What if we did this with an oxygen on the top and an oxygen over to the side?
Oh, I see. I know what you're getting at. The problem is, of course, is that this word right here doesn't work then because it's repulsion. Because, folks, these double lines are electrons, right? A single bond is a pair of electrons. A double bond is 4 electrons. So this is actually 4 electrons. And the point is the electrons want to stay away from each other. Here they're kind of closer together.
Yep. And these ones here are even closer together as well.
Yeah.
So the reality is if you were to put them in this state right here and they like stay there, on their own they'd be like, and they'd end up like this.
Yeah. Because, folks, you know this. You play with magnets. Magnets have positives and negatives, but in this case we have electrons. They have a negative charge. When you put a negative, they want to repulsion. They want to stay as far away as each other as possible. So the Vesper theory is really simple. You want the electrons to stay as far away as possible. That's the deal. As far away as is physically possible. So let's see if we can figure out that in terms of a shape with a molecule that I want to draw.
Okay.
So let's draw a molecule. So I'm going to think of a real simple one. It's CH4. So carbon has 4 bonds, and they're all, like this. So I want to get them as far away from each other as possible, Mr. Dmitrowicz. So I got to believe that's the best way, because valence, electron, pair, repulsion. My electrons are as far away as physically possible. I can't get further than that, right?
Pretending that there's electrons around each of these, that seems, in a two-dimensional world, you would be given a gold star.
Wait. I don't live in a two-dimensional world.
Yeah, that's the kicker, right? So we aren't in a two-dimensional world.
So how could you draw that? What would it look like in a three-dimensional world? Could you draw what that would look like?
I could, but probably better if we show it to you in the next video using models. But we could do this by causing some of these atoms to come out of the board at us, and some of the...
So let me make an attempt, Mr. Dmitrowicz. So let's say I have the carbon, and I do a hydrogen here and a hydrogen here. So these are in the plane of the board. And then I can, dashed line means it goes behind the board, and thick line means in front of the board. And this is actually one of the shapes. And if you actually do the math, each of these is 109 degrees. Every single angle is 109 degrees. That's better than 90. For
those of you who are a little retentive, and you know who you are, it actually is 109.5. I don't know if we want to add the 0.5 in there just to...
Right, fair enough.
There you go. For when you're reading the textbook, you want to come back.
By the way, that's called a tetrahedron, or tetrahedral shape.
Either one.
Yeah.
By the way, we didn't mention this before. He has the gift of drawing molecules. He's the one to be modest here. But in his head, he actually did the Kelter strategy. So if you're wondering how did he get this, on the side, he did valence, happy, and number of bonds. But he's just brilliant that way. And so he got that structure from this. So heads up, whenever we want to draw shapes like this, three-dimensionally, you've got to be able to draw your Lewis structure first. And in order to draw your Lewis structure, you have to know how to do the Kelter strategy.
So I know there's a couple of important terms that we've got to define.
Let's hit those right now.
So let's do a couple of examples. So if I've got water molecule, might be a good one. So
Sure.
if I'm drawing the water molecule, it turns out this is the shape. We'll talk later why it's that shape. But there's some important terms. So what are some terms? What's the first?
Why don't we
term?
talk about lone pairs? Lone pairs
Lone
are exactly what you think they'd be. They are pairs of electrons that are by themselves. They are not part of a bond.
So if I draw this structure, which ones are the lone pairs, Mr. Dmitrowicz?
Well, as being a teacher, and I'll hopefully get this right, but right here and right here,
Why?
those are our two lone pairs because they are not part of an actual bond. In fact, we sometimes call those non-bonding electrons. And we call things that are part of a bond, we call those bonding electrons. I know that's highbrow stuff. So lone pairs are sometimes known as non-bonding pairs, and bonds are sometimes known as bonding pairs.
So lone pairs are dots, and bonded pairs are lines. But what if I've got, like, we had this one earlier, carbon dioxide. What do you do with that one? I can see the lone pairs here and here and here and here, but what's the deal with that?
So here's what's really important, and this is incredibly important. Whenever we're talking about affecting the shape, double bonds are the same as single bonds. So both these here and these here, we refer to them as bonding pairs. They do not count
So
extra.
that's a bonding pair, even though there's 4 electrons.
Correct.
Right.
Now, there is a term that's probably the most scary of all of them. We call this effective pairs. And effective pairs refer to both lone pairs and bonding pairs. A better way of saying this is this. We need to know what things are attached to a central atom. So both our lone pairs of electrons and our atoms count as effective pairs. So if I looked at this structure right here, I have 2 lone pairs, that would be 2 effective pairs, and then I have 2 atoms attached to this central oxygen.
So that's 4
Effective-
effective pairs.
4
1,
effective
2, 3, 4. This one, though, has 1, 2.
Correct?
Because there's no extra electrons on the carbon. Even though there's technically 8 electrons, effectively there's
only 2. And incidentally, we are only working at the central atom. So this is the only one we care about. You might look over here and go, well, how many effective pairs are there on this oxygen?
3.
Yeah, wouldn't that be
1, 2, 3?
1, 2, 3, right? But we only care about the central atom here because what we're going to do next is we're going to show you how it fits. Now, this delightful diagram he just did, within a video or 2 from now, you're going to be drawing these exact same structures.
So that's how you do Vesper.
So we went all the way from British accent until the very end, and now you bust it back up.
Vesper.
Bloody hell. All right.